Okay. Again, these test strips, this is some of the THF that had come out from the column here. This has nothing to do with the synthesis. I'm just trying to show you, again, testing for peroxides is very important. And so, actually, since this is an enzyme, I can't just go sticking this into THF. These enzymes need water. So, there's a few things you can do. You can spit on it, okay? Get a little spit on there, give it a little water. Or you could just dunk it very gently into one little dunk with water, shake it off. The key point is it has to be wet or else you're never going to get a reaction to take place. Now we can just dunk it quickly, bingo, into the THF, and I see nothing. I see nothing. Okay. So, again, what are we talking? Less than 0.5. I mean, it's not even registering anything, if you can see. Anything over 10 ppm, this is ppm down here. Anything over 10 is considered dangerous. So, again, we're showing nothing, absolutely nothing. Okay? And as you can see, it can go way up. It'll measure as high as 100 ppm. So, again, another proof that our THF was good and had no peroxides. Okay, very good. All right, while the coenzyme A reaction here to make the CoA derivative is stirring, you got 20 minutes to clean up. So we're going to clean up. It's better to clean these two syringes that we used, especially the one with the ethyl chloroformate. You don't want to be using it with water because they're not miscible. So you're not, the best thing to do is acetone, right? Because ethyl chloroformate is really not soluble in water. Triethylamine has some solubility in water. But again, I'd clean these guys with acetone first to be sure the organic is out, and then hit it with water. And you can always put away the syringes with water, fine. And they're perfectly fine as long as it's DI water. If it cannot be sitting, they cannot have been sitting with a buffer. Because then the buffer will crystallize inside, or maybe due to water evaporation, and you can, throw your syringe out the window because it's now going to be stuck and you'll never get it out. So again, anytime your syringes have touched organic stuff, I prefer to wash it with a little bit of acetone first, and then some water, and then you can store it with just water. Having seen water last is fine. DI water, of course. DI water. Okay, very good, and everything else pretty much goes away while we're just stirring. Okay.
Alrighty.
Okay, after we've been stirring here for 20 minutes, we want to add just 1 drop of 6 molar HCl for this scale reaction. Okay, and that basically gets rid of all the bicarb. And so again, we always, whenever we add something strong, strong acid or strong base, you always want to add it while it's stirring, so that the concentrated acid or concentrated base is dissolved and diluted immediately. Okay, so again, right down the pipe. That's it. 1 strong drop of of 6 molar HCl, and just for the heck of it, over here we have, you may want to go over here, we have the pH meter, pH paper, and here's the color wheel for it. All you need is a teeny tiny piece of it. This stuff ain't cheap, so actually it's not a bad idea to just get, all you need is a tiny, you can do it like less than a microliter and get an idea of what the pH is. So basically I just want to be sure that we're on the slightly acidic side. We don't have to be all the way acidic, I just want to be sure the pH is not above 7. Because if the pH is above 7, then as we concentrate it by rotovapping off the pH, the THF, we have to get rid of the THF, and so that'll be going from a total volume of 5 mLs down to 2 mLs. We don't want things to concentrate to the basic side. We want things to concentrate to the acidic side, because Again, the CoA derivative thioester linkages, base labile is base, is not stable to base. So again, we can just, I just, even just using a tip here, just take a tiny dip right up there, and I can just look right on here, and yeah, that's looking pH 7, right like there. Oops. Actually, even less, pH 5 or 6. Again, as long as it's not above 7, which is easy to tell with this pH paper. All right, good. Now we're ready to just rotary evaporate here to get rid of the THF. Okay, so we're here in the biochem teaching lab using the rotary evaporator to remove the tetrahydrofuran. Now, tetrahydrofuran has a much lower boiling point than water, and so it will evaporate mostly first, and then most of the water will stay behind. So again, we started with 5 mLs total volume in here, 3 mLs THF, 2 mLs water. So we expect it to go down to less than half of the original volume. And the way you know you're done, really, is because you'll see no more bubbling of evaporating solvent, and basically the solution that's left with the CoA derivative in it looks like it's not really doing anything. Okay, so what do we need to know? Well, first we got to turn it on. There we go. And this is the speed at which the rotary evaporator will spin here. You'll see in a second. We don't need to put the temperature on for the hot water bath. This is a hot water bath whose temperature can be very precisely controlled. We don't need to put it on because when we pull a vacuum here, the water aspirator will be lowering the pressure in here so that the THF will in fact boil away at room temperature. And in fact, you don't need to heat it up. You'll in fact do yourself a disservice by heating it up because the THF will evaporate too quickly. So basically, this is just a heat sink. I know it doesn't sound like a heat sink, but it is. It'll because this water is warm enough at room temperature to get the THF to evaporate at the lower pressure. All right, so here we go. We have to turn the aspirator on. This is basically, can you zoom in here?
Yeah.
Yeah, this is basically just this when the opening here, right where my thumb is, when the opening here is right up against glass, then obviously it's a closed system. When you go like this goes open to here, which is used for some other purposes. So this is now open to the system. This is closed to the system. So you want to keep it like this, closed, or else you'll never draw a vacuum. Now again, never assume anything's working right. Always be sure that in fact you are pulling a vacuum. So how do you know that? Well, you put your hand here and you get a little hickey, okay? So, you obviously the vacuum is working. And so make sure the water is on full blast here so you get the best vacuum possible. Here's our solution. Now again, if you happen to have used the 1922 glassware, which refers to the dimensions of the ground glass joint, then you're going to need this adapter. Okay, this goes from 1922 to a larger, more common 2440 ground glass joint, and the reason we need to do that is two reasons. Well, one reason is that this is 2440 here, but the real reason is because we want to have a splash guard in between. And a splash guard is what? This is basically in case this happens to bubble up. At least we have stand a chance of catching our material so it doesn't go over into here and go all into the, that's not what we want. So the key point here is we'll be evaporating THF from here. You probably won't even see any collect, and the reason is because there's so little of it, it'll just basically evaporate and wind up going down the aspirator. So what's the key points? The key points is that we hook it up just like this. We're setting it up, and now it's a closed system. Here's the aspirator pulling. Here's where large volumes of solvent would collect. This is the water cool. Oh, we forgot to turn the water cooling on. Sorry. As you can see, there's the cooling coils. Again, they're just regular cold water out of the tap. Now, because we're only rotary evaporating 3 mLs of THF, I don't expect to see very much happening here. But when you're doing large volumes, you sure definitely see a lot of material here dripping down into here, and this would be collecting your distillate. Okay, so right now I can hear the vacuum. The aspirator sounds different, and in fact, if you went to try to pull this off, you couldn't even pull it off because of the vacuum. All right, so now what do you want to do? Ooh, it's even boiling already. Can we see that?
Yeah.
Then come on over. Okay. We are boiling already, but the key point here is that we want a rotary evap. We want to rotate. Why do we rotate? Well, we rotate so that you increase the surface area, so that the entire inside of the flask here is coated with a very thin amount of the solvent to be evaporated. So by spinning, you effectively double or triple the surface area over which you have available to air to be evaporated. Okay, now again, you see what I do is I tap it sometimes. You notice again, THF is a pain sometimes. Sometimes it tends to bump like this, which is why I keep the stirring bar in there. That kind of helps it seed it as helps seed the bubbles. Sometimes people just use nitrogen gas flowing to blow away the 3 mLs, right out of a nitrogen tank. You know you're evaporating because you feel here, and this is cold now. Why is it cold? Well, it's cold because the warmer molecules have evaporated. So what's left must be colder than what you started with. So there we are, we're evaporating. Now, if it gets too cold, you'll be sitting here all day, right? So that's why you can let it warm up. Can you see here from there? All right, I want to see. You want to be sure you can use the lever down on the bottom here. Wait, somebody broke. Oh no! Hold on. You can submerge it. Can you see that? And that'll keep it at room temperature as long as you're spinning like that. So it will never get any hotter than room temperature and never get any colder than room temperature either, so it helps to speed up the evaporation. Because like I said, if you kept it out here, it would get very cold, and the rate of evaporation would be much lower. And so here you're constantly supplying heat from the room temperature water to keep it at a constant temperature. Now you can see now it's starting to cloud up. That's okay. That will fix later. But it's obvious that it's still evaporating. Notice we don't have to spin it 100 miles an hour. You can spin it just regular, nice and gentle. And again, you just keep your eyes on it to be sure that you're not splashing up into it. Yeah, THF is notoriously a pain in the neck when it comes to a rotary evaporating. It tends to do this. And again, you know you're done because you won't see this bubbling anymore when you're just left with water. Okay, well, our reaction product here has been sitting here several minutes like this without a single bubbling event. And so I can tell you it's pretty much done now. Now, you can't really over-evaporate. Sure, if you left it here for another hour or two, you'd have no water, and it would be, you don't want that either. So again, we have approximately 2 mLs in there left right now, and you pretty much know you're done because nothing's happening for the past several minutes in terms of any bubbling. Okay, so you're done. So what do? You raise it up out of the water. There it is. Don't worry about the cloudiness. Depending on the CoA derivative, the solubilities and the are pH dependent, and sometimes you need to tweak it to get it back into solution, so let's not worry about that. It's okay that we have that it looks like that for now. That's fine. All right, so what do? First thing we do is we stop the spinning, and then we slowly let the air in. Okay. All right, so now that we got the air in, we can shut off the there, and also shut off the cold water for the condensing coils. And I mean, that's it. We're basically done. I mean, now we just gotta get it off, and okay, there it is. This one happens to be a little milky, but that's okay. We're done.